Hi, my name is Daniel Maguire and this is my Evolutionary Computation project on the income classification using genetic programming analysis on the adult dataset. So the goal of this project is to classify individuals based on their income levels using the adult dataset. I'm using genetic programming to predict whether the individual's income exceeds $50,000 annually. The task isn't just a classification problem, it's also a study into the effectiveness of GP as at classification tasks, and specifically on real-world data. So the adult data set is acquired from census data and includes a range of demographic and economic features. Each of these features has the potential to influence the income level, and all are potentially important. So, in addressing missing values in the dataset, I chose to remove rows with missing values. I made this decision based on the idea that keeping data complete and accurate is the most important thing, and there should really have been minimal data loss. So, I also introduced a new feature called net capital, which is calculated from subtracting capital losses from capital gains, and this was aimed at providing a clear understanding of the individual's financial status, giving that directly to the algorithm, in the hopes that it would be able to calculate more effectively. My test indicated that the model performed better when using this consolidated net capital feature, rather than maintaining the capital gains and losses as separate variables. I also changed the age feature to be categorized into 3 groups instead, so young, adult, or retired, and this was designed to simplify this data and capture the influences of age on income across different stages in life. Grouping ages simplified the data, and it was supposed to make it easier for the model to interpret these differences. I used a standard scaler on the numerical columns, hours per week and net capital. The goal was to ensure that these features were standardized, meaning that they would have a mean of 0 and a standard deviation of 1. Originally, I was using one-hot encoding for the categorical features, but I want to see if other encoding methods might have improved the accuracy on the test data. So after researching a few different methods, I was interested in using target encoding and cat boost encoding, and I created a setup, 2 different setups using cat boost and the other 2 setups using target. Okay, so let's take a look at the fitness function. So the idea is that the function processes each row of the encoded training data x train encoded. So in this function we also check and count infinite and not a number values. These values often result from invalid mathematical operations, so we want to count them and try to remove them from the learning process. So if invalid outputs exceed 5% of the training data, a large penalty, type error penalty, is applied. This rule helps penalize poor solutions, but also allows some room for occasional errors. So within the fitness function, we also take the predicted values and convert them to binary using a 0.5 threshold. So accuracy is measured by the proportion of correct predictions from all the valid predictions, excluding those with infinite or not a number values. Okay, so let's take a look at the function set. While developing this model, I tried a few different function sets, starting originally with arithmetic, trigonometric, and exponential operations. And using these alone, my results were decent, but I wanted to expand the model's computational capability. So I added a conditional operator to allow decision making, and to go along with that, I also added comparison and logical operators. Finally, I wanted to see how the model would perform if I gave it looping capabilities. So to achieve this, I added a for loop function. Now let's take a look at the model's parameters. The population size of 100 has a balance between diversity of solutions and computational manageability. Larger populations do offer more diversity, but at a cost of increased computational ability. And setting max generations to 100 provides enough iterations for the population to evolve and converge while preventing excessive computation as well. So for crossover, I tested 0.4 and 0.6. I would have liked to test more. 0.7, 0.8, and 0.9 were part of my test, but due to time constraints, I had to settle for this reduced crossover set. And for mutation, I tested 0.01, 0.1, and 0.3. So, maintaining a Hall of Fame of 10 individuals helped preserve the best solutions across multiple generations and runs, and I found that 10 was best in this case. So, as for my evaluation and optimization strategy, I split the dataset. I did two different splits. I had an 80-20 split and a 70-30 split, and I have two different setups for each. So for optimization, I have three guesses, which are iterations, and they're executed on each parameter set. And this allows the model to explore a variety of evolutionary paths. And due to the stochastic nature of these algorithms, it's worth running them multiple times to get a better idea of what's going on. So I also added adaptive termination, and this is based on the validation error and used to try to reduce overfitting. To do this, it's basically just when the delta between the fitness and the validation becomes too high, the model exits the run. Also, when the validation does not achieve the minimum threshold, we do exit that set of runs as well. Then to take a look inside the GP algorithm, so the way we're using Hall of Fame is to track the best solution multiple best solutions over multiple generations and runs on a particular parameter set. So I also use dynamic error thresholds for model refinement, and this is basically just for run 1, I'm setting a more strict delta between the validation and the fitness. And then after that I'm a bit more lenient, and I found that this worked pretty well. So I also added stopping criteria based on how good or bad the improvement of the validation and the fitness are. So if the delta between the fitness and the validation increases or gets large enough, then we can exit, and that will be our stopping criteria. We also stop the runs if there's no substantial improvement seen. So the fitness evolution is also plotted and for a visual understanding. So our optimal settings were having the crossover set to 0.4 and mutation set to 0.1. We generally got consistently above average outcomes using this combination, and there's always a balance of stability versus variation. We found an interesting balance here with 0.4 and then having a higher mutation rate of 0.1. And yeah, so overfitting did occur, potentially due to the encoding methods that I used. Target encoding is especially known for. I need to add regularization, and that will be for future. So, and then yeah, evaluating off Kaggle data was generally lower, and the higher we got, like past 0.79, the more off it got. I believe this was a successful application of GP, with around 0.79% accuracy. Not amazing, but in the right direction. Crossover probability at 0.4 and mutation at 0.1 consistently led to above average outcomes. The lower crossover probability of 0.4 seems to strike the right balance in mixing genetic information without causing too much disruption, and then at the same time somewhat high mutation of 0.1 helps introduce enough traits to keep the solution evolving and improving. Finally, overfitting is a big problem here and needs to be addressed going forward. And finally, for future work, I think I will focus on feature refinement, and I also want to look into more advanced genetic techniques to see if they could help, but really the main thing I need to look into is techniques to combat overfitting. That is my presentation. Thank you very much.